Welcome back! If you were surprised by the last video, where instead of our Intel CPU, I was talking a lot about the Raspberry Pi Pico microcontroller, then now it is time for me to explain my reasons. But before I start, let me first thank PCBWay for helping me create this video. PCBWay is a PCB prototyping manufacturer. Multiple PCBs are their star products, ranging from standard PCB, flex PCB, advanced PCB, PCB assembly service and others. They also offer one-stop solution service. Apart from the inner PCBs, the outer enclosure could be finished as well, such as 3D printing, CNC machining, injection molding and others, covering different kinds of materials. With PCBWay, makers can realize their ideas into real projects. Apart from that, their open source community is pretty popular among the creators, especially the shared project section. Many PCBWayers have shared interesting electronic projects there. If you are interested in any of them, you can get the boards there directly. Check them out at pcbway.com. Thank you PCBWay for making this PCB for us. And before we start putting chips into the empty sockets, let me tell you a few words about my future plans. I decided to separate this series of building this computer using ATC188 on the PCB into a separate playlist, and I'm gonna just carry on building and programming this computer, which doesn't mean that I forgot about the old computer, the ATC88. Here on the breadboard, it's still here, waiting for more chips to be added to it. So in the original series, I will carry on with the breadboard computer using ATC88, and I will add more peripherals, more chips, and explain how they work and how to connect them to the computer. So okay, now let's get back to the PCB. If you saw my last video where I was talking about the PIO block in Raspberry Pi Pico, it wouldn't come as a surprise if I told you that that's exactly what we're going to put into this socket here. So let me do this right now. That's a Raspberry Pi Pico, and it's going here. There are two more sockets here, which I will populate in a second. Just need to mention what the Pico is doing here. I decided to use it in the computer because the PIO block is great for quickly reacting what's happening on the GPIO pins and sending data via those pins. So I thought it would be perfect for using this chip as a peripheral in our computer, talking to the main CPU, using the data bus and the usual signals, RD, WR and so on. But the problem is that GPIO pins in Pico use 3.3 volt logic. They are supplied with 3.3 volt, not 5 volts like the whole rest of the system. And even worse, the GPIOs do not tolerate 5 volts on their input. So if I just put straight data bus to the GPIO pins, they could be damaged. They are not tolerant of 5 volt levels. And that's exactly what these two chips will do. These are usual 74245s bidirectional transceivers, which can just transfer 8 bits of data both ways, and there is a pin switching the direction of the data. But they are a special version. It's another newer family of the 7400s called LVC, and this chips work in 3.3 volt logic level, but they are tolerant of 5 volts, so you can put 5 volts to their inputs and they will work correctly and recognize the logic levels, and at their outputs you will see the the newer 3.3 level, which is acceptable for our Pico. So one of the chips converts the data bus, 8 bits of the data bus, and the chip here, which is identical, is used only really in one direction towards the Pico, and it just converts a few signals like chip select, WR and RD, and ALE, so address latch enable. So let me explain why do I need the ALE signal in the Pico. I'm going to use the Pico as a few different peripherals, really. So I need some address pins. And if I wanted to use the separate GPIO pins for addresses and 8 additional pins for data, I would run quickly out of the GPIOs available. The standard Pico has 26 GPIOs available. I want to use some of them for the peripherals, which I'll talk through in a minute. I just simply couldn't do this. I couldn't use separate GPIO pins for address lines and 8 GPIO pins for the data bus, and then 3 pins for the CS, WR and RD. And also I need to talk to that CPU the other way, so I need 2 more pins for the ready signal, because obviously sometimes we can't just serve the data instantly on the data bus without wait states. So I need the ready signal and the interrupt request signal. I will need to, like any other device really, like the timer or any other device, sometimes I need to request an interrupt in the CPU to let it know that it needs to read some data coming in from our peripheral. So I would run out of the GPIOs, and therefore I thought, well, we already have multiplexed data and address signals in the data bus from the CPU. So even if I've got those 573s here to latch the address and using it in addressing all the other chips here, I decided to use the multiplexed data and latch the address again inside the Pico, and that's why I need the ALE signal. So in the PIO program, which handles all the transmission between the CPU and our Pico, which I will discuss in a minute, you'll see how it's done. Okay. So we know why we need to use the LVCs. They convert the 5-volt logic from the CPU to 3.3-volt logic in the Pico. But what about the data bus when it's being read from the Pico? And what about the ready and interrupt request signals, which are at 3.3 volt level? And they are directly connected to the CPU, and they need to drive the CPU's inputs. So if you look at the datasheet of the ATC188, you will see here in the second row the VIH symbol, which is a voltage allowed for the high level or any input. And as you can see, the minimum voltage is 2 volts, which is far less than 3.3. So I decided to drive the inputs of the CPU straight from the Pico, or in case of the data bus, straight from the LVC, which produces, of course, 3.3 volt logic levels. Okay, so what the Pico will be doing here in our computer? You can see some pin headers here and there. So apart from obvious like serial port, which will be implemented in the Pico, and then the CPU could talk to the Pico using the I/O ports. There is also a pin header for an SD card module, something like that. So we can slide it in, and you can use this SD card as a hard drive. That's my plan. Also, the other pin header is to be used with the RTC module, which works using I2C bus. But I decided later on to not using this, and that's because I just realized that the original RTC chip, the DS12885, is still easily available to buy. Also, the 1287 version, inside this big case, it contains the battery which would keep the memory and the RTC feature working, even if it's completely off the device. As you can see, this one is produced in the 1988, so I'm sure the battery is now completely dead after 35 years. But I will use this RTC in the new version of this board instead of the I2C here. But just for tinkering, there is still I2C available in this pin header. So most importantly, hard drive using SD card. I'm going to implement hard drive controller in this Pico, serial port or UART. Also, because the Pico may work as USB host, so you can connect devices to the Pico and it can talk to them, I decided to use it as the keyboard controller as well. But more about these I will talk in the future videos in this playlist, in this project, and I'm already designing a new version of this PCB. Because I unfortunately made a few mistakes on it. The one which I already told you about, the timer 0 input, which was grounded, the pin 20. I told you about this in the previous video, but there are more. For example, I'm using the S2 signal from the CPU to decode the chip select for RAM, and I used it straight away from the CPU, but it needs to be latched like the address lines because it's being removed too early and may cause problems reading or writing to memory. So I had to latch it. Here's the fix. I just took the S2 and latched it using unused bits of this 573. More fixes are visible on the back side of this PCB. Unfortunately, I found that I made a mistake in connecting to the Pico, and so I had to just solder one OR gate on the back of this PCB. I added some decoupling capacitors as well. So there are a few things which need to be fixed, and I decided to change a few things as well, but that's all is going to be done in the second version of this PCB. There are some breadboards on the top. Currently they are holding only our text LCD, but I'm planning to add something to this computer in one of the future videos. We'll talk about it later. Here is the current schematic of this PCB, including all the fixes. I've already told you roughly how our Pico is gonna communicate with the main CPU, but now let's look at the schematics. Here are the two LVC245s. One of them, as I mentioned, is the transceiver for our data bus. Well, in fact, it's not only data bus, it's the multiplexed address and data 8-bit bus that is gonna go to ports 8 to 15 on the Pico. The PCS0 is the chip select for the I/O straight from the CPU, and it enables the transceiver, so it talks on the data bus only when the Pico is chosen by the CPU. It's a chip select like any other. If it's high, if it's inactive, then the transceiver is in high impedance state, so it doesn't talk and doesn't read, doesn't write any data on the data bus. The other LVC, I'm using only 4 bits out of 8, so as you can see the rest is just grounded, and those are the control signals. So ALE, the address latch enable to demultiplex the address from the data inside the Pico, chip select again, because we still need to be monitoring it in our PIO block, and you'll see the program doing that in a second. And the WR and RD signals, they are all going to the GPIO pins number 2, 3, and then 6 and 7. I didn't start from 0 and 1 because these, as you can see, are reserved for UART, so serial ports, and the pins 4 and 5 are reserved for I2C controller. You've seen that 4-pin header on the PCB. That's for future expansion. We can add some I2C devices, some sensors to our computer. I just decided to save it for later. Pin 6 and 7, as I mentioned, WR, RD, then 8 bits of the data bus or multiplexed addressing data bus, then some other pins of the GPIOs on the Pico are reserved for SPI controller, which will talk to our micro SD card, and the other two are another I2C talking to the RTC. That's what's on this schematic, but as I mentioned, I decided to use the old original DS12885 RTC directly on the CPU's data bus. I will talk about it in the other series. We will pop it in our ATC88 data bus on the breadboard the other time. Okay, the other LVC, the one which translates the logic levels of the control signals, is kind of hardwired to talk from the left-hand side to the right-hand side only, because these are input signals for our Pico always. The data bus, though, needs to be, of course, switched between reading and writing, and I added this OR gate, which you saw on the back of the PCB because I forgot about it. Obviously, the data bus needs to be read by the Pico in two cases: whether the CPU wants to write to it, or whether the ALE signal is active and the Pico needs to read the address, part of the address, the 8 bits of the address put on the multiplexed lines. So that's what this chip does. The output pins from our Pico to the main CPU, pin 20 on the Pico ready and 21 the interrupt request, are output signals which go straight to our main CPU directly. Okay, let's finally have a look at our PIO program for our multi-IO peripheral. I called it bus control, and if you have seen my previous video about the PIO, you already can tell that in this program I'm using optional site set to change the state of one of the GPIOs. If you have a look here, you can tell that the site set bit I'm setting is the ready signal to the main CPU, the 8188. I also defined other GPIO pins I use in this program, and I'm doing this in the PIO section, not the C section, for a simple reason, because those definitions I can use both in the PIO, like here for example, as well as in the C part of the program. The definitions, the macros, are prefixed with the name of the program and the underscore, and they are defined for the C code as well. So it's a good way to keep everything tidy, and you can easily change those definitions in one place, which is the PIO program here. Okay. These are comments helping me to remember the pin mappings. We already looked at the site set, that's for ready signal. The bits which are set to out, sometimes, not always, is the data bus, the 8 bits of the data bus, and the rest of the pins we read, so they need to be mapped as the input pins. So let me quickly scroll to the initialization function, C function, which looks very similarly to the functions which I showed you in the examples from the previous video. But we have more pin mappings, which is quite interesting to look at, because in the previous video I used only site set and out, because we only used really one bit, one GPIO pin to drive the LED modules, while in this program we're using 14 GPIO pins. I think it's 14 in total. We've got other mappings as well. The in mapping, which really tells the PIO which pin is the starting pin to read the data from, And as you may notice, in contrast to the out pins, when you need to define how many pins will be outputs, in our case it's only data bus, so it's 8 pins, the in pins function doesn't have this parameter, the third parameter telling how many bits. And that's because you can read all of the pins in one go. The registers and the input shift register is 32-bit long, so it can read all of the pins in one go. The function, only thing the function does is to define which pin is the least significant bit to read. And if we, for example, define it as 26, for example, and read more than available pins on the RP2040, the numbers will wrap up after 31. So it will go, for example, from 26, next bit would be 27, 28, 29, 30, 31, and then 0, 1, 2, and so on. So the numbering wraps up around the 5-bit value. After 31 goes back to 0. In our case, the lowest bit we're going to use as an input is the WR pin, which you saw the mapping and all the connections on the schematic just a minute ago. So you may ask, oh, the ALE and CS pins have lower numbers, so why don't you define the lower number for the LAE number 2? And that will become obvious in a second. The other interesting point I'll try to make in this program is that you may use shift registers in different ways, really. Usually you use them to transfer the data between the CPU, the main CPU, and the GPIO pins. But I also used output shift register in a different way, which we'll get to in a second. Okay, let's go back to the C initialization code, because there is another interesting mapping which is not used that often, which is the jump pin. You can designate one single pin to be checked and then conditionally jumped based on its state. So that's how we really read the ALE pin, not via the input functions, but just simply checking and conditionally jumping if it's active or not. As you can see, in this case, we jump if the pin is active, which means if it has the state of 1. Okay, so let's analyze the program line by line. This is also an interesting line, the wait 0 GPIO and the GPIO number. What it does is to wait until the specified pin goes to the state which is defined here. So effectively, at the beginning of our program, first thing which we want to do is to wait until the chip select goes low, goes active. So we're not doing anything really in this program until our peripheral device is selected by the active chip select. Until then, the PIO program stays here and waits, doing effectively nothing, just waiting for the chip select to go low. If it does, which is the first kind of stage of the bus cycle, which involves our Pico as the peripheral, it goes line below, which checks and conditionally jump. If the ALE is active, it jumps down to the label called ALE active. And if not, it just passes to the next instruction, but we're going to get to that in a second. First, let's analyze what happens in the program when the LAE is active, which means that the CPU is serving us the current address on the address and data bus. Effectively, we're reading the 8 bits which are multiplexed with the data bus, which is more than enough because really, if you remember, the 8188 allows for each chip select to be mapped to 128 ports, IO ports, which is 7 bits. We have the 8 bits, but we're kind of gonna ignore the 8th bit of the address anyway. But what happens here? This instruction move Y pins does two things. As you can see, it also side set the ready signal. If it does set it to 1, it means that we are signaling we're not ready yet. We'll get the ready signal back to 0 when we're ready reading or writing the data. It's a signal for the 8188 to wait for us until we're ready with the whole bus cycle. Move Y pins reads all of the pins as inputs, starting with our defined pin, which is the WR, the lowest pin number 6, to the Y register. And then we are reading the Y register into the input shift register, and specifically 10 bits of that. I just need to explain two things now. Why 10 bits? That's because we read from the WR, we need to read these two bits, WR, RD, and then 8 bits of the data bus, which come straight after these pins. So it's in total 8 plus these two, 10 bits. So that's why we read 10 bits from the Y register into the ISR, input shift register. Now the question you may ask is, why not doing this in one step? Why do we need the Y register on the way? Here is a similar line which does the same thing in one go, which reads pins straight into the input shift register. And that will become obvious in a second, but we're using the Y register as a temporary marker that the ALE was active, and we've got the address part from the bus already read. So the only thing it does, the PIO program does in the ALE active, is to read the 10 bits from our inputs, WR, RD, and the 8 bits of data, storing in the Y register and input shift register, and then jump up back to the idle loop. And obviously, because the ALE is active for around one whole clock of the 188, this program may then work in a loop here between the idle and ALE active, but that's fine, because so it may read those bits multiple times. But that's fine, because the only thing we care about is that the 10 least significant bits of the input shift register contain our input signals, most current input signals, let's say. So this goes in a loop until the ALE becomes not active, and therefore the jump wouldn't be taken. And the next step is to, as you can see, check WR. So this part of the program starts looking into our input bits, knowing that we already passed the first stage of reading the address from the address and data multiplexed lines. So now we're looking whether the CPU 8188 wants to read data from our peripheral or writes into it. First line explains why we had to use the Y register. The only purpose of it is just to mark that we've already passed the ALE signal stage. And how, you may ask? It checks whether the Y is 0, not Y means if it's jump, if it's 0, back to the idle. The Y register would contain anything but 0 only when the ALE signal was active and we read the input pins. Why, you may ask? We could address the I/O port of 0, and then Y would be 0. Well, no, because we read not only 8 bits of data in here, but we read 10 bits together with the WR and RD. When the CPU reads, then the RD is active low. When it writes, then the WR is active low. But they can't be low at the same time. So one of those bits must be 1 at any point in time. That's why we read into Y all the pins, and we know for a fact that if we've gone through this part of the program, then the Y register would not contain 0 for sure. And that allows us to decide whether to carry on with the program or just go back to the idle state. All right, so first, as the label says, check the WR state. How we do that? Well, now this time we read our pins into the output shift register, and since the lowest number of the pin is WR, the first bit in output shift register, the least significant bit, would be the WR. We are shifting out from the output shift register this one bit to the X register. Then we're checking the state of the X and conditionally jump to check RD if it's not active, because the jump X minus minus means check if the X is not 0 and jump only if it's not 0, and post decrement. You may ask, why do I need to post decrement the X register? Well, I don't have to, but that's the limited encoding of the PIO instruction gets in the way. You can check if the X or Y is 0 and then conditionally jump like we did here. But for the check, the opposite check, where jump if the register is not 0, the only encoding is with the post decrement. So we don't care about post decrement. It's just the way the PIO instructions are encoded. It effectively means jump if X is not 0. If the WR is not active, that means we need to check RD. Maybe the CPU wants to read from us. And the label is here. The next bit to shift out is the RD, so we're shifting out to the X register, our RD bit, and doing the same check again. So if it's not active, whoops, something's wrong, we're going back to the idle, because the CPU neither reads or writes. But if it is active, the RD is active, it just falls down here. And since we already have the address to be read from in our input shift register, then we simply push it to the FIFO to be read by the main CPU, the ARM core, on our RP2040. If I'm saying the CPU in the context of PIO programs, I usually mean the ARM core inside the RP2040, not our kind of main CPU in our computer, the Intel 8188. But I'll try to explicitly tell which CPU I'm talking about. So, we're pushing our address read previously from the input pins here to the FIFO, and then we raise an interrupt. Again, interrupt to the ARM core within our Pico. That's interrupt number 1. We are also using the other interrupt, number 0. That's for writing. We're going to get to that in a second. And straight after raising this interrupt, we are changing the directions on the data bus, because by default we're reading from the perspective of the Pico. We are reading, waiting and reading the address bus and then the data bus if the CPU, the 8188 CPU, wants to write to us. But if it wants to read to us, that's the only case when we need to change the direction of our GPIO pins as outputs to serve the data to the 8188 CPU. How do we do that? Well, you could do this straight away by move pin dirs. So instead of doing this in 2 steps, we could do move pin dirs and then immediate value. But that value could be only maximum 5 bits. Unfortunately, we need to change the direction of 8 bits, the whole data bus. So we need to do this via output shift register, and that's the case where we use output shift register in a different way, not to transfer any data via GPIOs to or from the processor, but only to set pin dirs, pin direction as outputs. And that's because of the feature of the not no, which, as you may remember from the previous video, sets all the bits to ones. So effectively, this function, this instruction, sets all 32 bits of the output shift register to 1. Well, we need only 8 of them, but we can just shift 8 of them to the pin dirs, which effectively changes the direction of the data bus to outputs. Why does it not change the WR and RD? Well, if you remember, here we've got this comment, and you can also see it here. We are setting the out pins with the lowest number, 8 pins with the lowest number of the data bus, which is pin number 8, not 6. Like in other cases. This changes the direction of our data bus to outputs and gets it ready for the ARM core and our PIO program to serve the data on the data bus to the 8188. In this moment, while we, after we have raised the interrupt, we hope that ARM core will do its work in the interrupt handler, and at some point it will push through the FIFO the data to be served to the 8188 via the data bus. And we're waiting for the data from the FIFO here in the pull block. If you remember again from the previous video, pull block waits, because it's a blocking call, it waits until we've got some data from the ARM core CPU via FIFO sent to our PIO program. If the interrupt handler sends this data, we can simply set the data bus pins to 8 bits received from the ARM core. And as you can see in the same instruction, we side set the ready signal for the main CPU, the 8188, letting it know that the data is ready to be read and it can finish its bus cycle. Then we simply wait in this loop until the 8188 deactivates the RD signal. So in this simple loop, we again read the input pins to the output shift register. We need to throw the WR bit, which is in front of the shift register, to null, so it means just throw it away nowhere. And the next bit is RD, so we check its state, and if it's not 0, if it's 0, not X means equal to 0, jump if it is 0, so if it's still active, loop around. And then we fall down to the reset bus, which sets the Y register to 0. This is important exactly for recognizing the next bus cycle and whether the ALE was active or not, like before. And we're just for sure side setting here for 0, because the reset bus is jumped from the WR part of the code, which we'll see in a second. So it signals the CPU, the 8188, that we're ready after writing to us. And also again, in the similar way to setting the direction of the data bus to outputs, here we're doing the same, but now this time we're populating the whole output shift register with zeros, null, not null, like here. Null means set the whole register to 0, and then out changes the pin directions of the data bus back to the inputs, and it wraps around to the idle state. So the only part of the code we haven't really discussed yet is the WR part of the code. We've already mentioned this, so if the WR is active, it falls under this jump, and this NOP and the wait delay, I used it just to make sure that the data bus is settled after initiating the bus cycle and the W goes active. And then again, we read 10 bits from the pins, 10, because again, we read the WR, RD, and then 8 bits of the data bus. So we read 10 pins of them. into the input shift register, remembering that this part of the code already stored the address from the CPU bus. So effectively, we will have in our input shift register at this point 20 bits of data, the 10 bits, the address, WR and RD, which we're going to ignore in software, and then the data the CPU, the 8188, wants to write to us together with, again, WR and RD, but we're going to ignore these as well. And what we do here is we push the input shift register, so the kind of address and the value being written to us via the FIFO to the ARM core, and then we raise the interrupt. This time, just to easily tell between reading and writing, we're using the interrupt number 0, and we wait until the interrupt status bit is 0, and that happens when the ARM core acknowledges the interrupt in software. We'll see the code in a second. So the code waits until the ARM core receives the interrupt and the data being pushed here. And then we just go down to the reset bus label, which we have already seen. I just realized that I could use the site set and signal the readiness of and the end of the bus cycle for the 8188 here, site 0. But since I've tested this program in the state which I'm showing you and showed you originally, I'm not going to do this change now. The only comment I need to make is that we cannot do the site 0 here. You may say, oh, okay, we raise the interrupt and then we wait so we can site 0 marking that we've done our thing on our side and we're ready. Well, the thing is, and that's quite important information, despite the fact that the wait and the PIO program waits on this instruction until the interrupt line goes to 0, the site set, and it's a comment on any instruction in the PIO which may wait for anything, the site set is always executed at the beginning. So even if the wait waits here, the site set would have been executed at the beginning when the PIO goes into executing this wait instruction. So that would be premature, and we shouldn't do this here. But we might do this here in the jump reset bus. It doesn't really matter. We're doing this here. I tested this program and it looks like it works. Okay, let's finally see the C code of this Pico program. And I will start from initializing the PIO. That is the function which is called at the very beginning. And you already may recognize some of the calls like these two. This just loads the program and initialize the PIO to use the program. Instead of using the definitions from the SDK straight into here, like PIO 0, for example, and state machine could be 0 because that's the only state machine we use on this PIO, I decided to separate all the definitions like that into a separate file, header file here. The other lines which we haven't seen in the previous video is to initialize the interrupt requests. That line links the PIO interrupt line number 0, and then we're just setting the function which will handle the interrupt, the priority, and enables the bit to the interrupt to be active at all on the CPU side. That's the PIO side, that's the CPU side. And that happens for the interrupt line number 0, which is for writing, hence the function name bus write handler, and exactly a similar thing for reading, and the interrupt number 1, the PIO interrupt number 1. For reading, and that just runs, starts the state machine running our program. let's go now to the handlers, both write and read. These just effectively formats the data being sent from the PIO program. So that's the function which reads from the FIFO, and really I use the loop, but effectively we should be getting only one 32-bit data from the FIFO. It's just again safe coding just in case something got lost on the way. So we read the data, and then we just extract the bits from the data, because in case of writing, remember, we've got the address in this 32-bit data, as well as the data from the 8188 sent via the data bus. So we are extracting those by just shifting out, and as you can see, this limits the address to 7 bits to 7F in hex, because we ignore the 8th bit of the address line, and then the value, and then we call our CPU bus write IO function, which just gets the kind of extracted data ready to be acted on. We'll see this function in a minute. And then we clear the flag, the interrupt flag, which means that we are done in the handler. We've noticed the interrupt in the first place. We've done our job, and you can go on PIO and do its thing. That's what the wait 0 IRQ0 does here. So once we've called this interrupt clear function, this wait would just pass on to the next instruction. The bus read handler is very similar, but in this case we have only address to be read from in the data sent from the PIO, and we then call a twin function to the CPU bus write IO, the CPU bus read IO with the extracted address, and its result, because, well, CPU expects, the 8188 expects some data from us, it's reading from us, so this function returns the data to be sent back to the 8188 during the bus cycle, and the data returned from this function we put to the FIFO, which then is pulled here from the FIFO and sent to the data bus of the 8188. And then we clear the interrupt flag as well. Oh yeah, one more thing. The time critical func is quite critical. It's a definition to tell the compiler to store the function in the RAM, so it will make the initialization code to copy the function with this definition from the flash to the RAM. That's because the Pico module contains a serial flash. The RP2040 doesn't contain any flash for storing programs inside itself. It uses the serial flash, which takes some time to read from. So we just want to make sure that these critical functions are being already stored in the RAM and executed from RAM for the obvious reasons, because we want to do our job as quickly as possible without any delays waiting for the flash. So that's the CPU write IO function, which is called from the handler, here. And the CPU bus read IO, which we'll start from, is here. For the test we're gonna make in a second, I defined two separate I/O devices. They are not very useful, really. They just test our program and if the whole idea works at all. So I defined two 16 bits port I/Os. One starts with the address of 0 and 01, and that's because when you read or write 16-bit I/O ports in the 8188, let's say you address the port number X, the least significant byte is read or written from the port number X, but the most significant byte is read or written from the port number X plus 1. So if you use 16-bit in or outs, it will effectively read or write two I/O ports, the X and X plus 1. So if we address port number 0 and use 16-bit transfer, it will effectively read or write. In our case, we're reading here port 0 and then 1. And that is, as you might guess from the names of the values of the variables, it generates Fibonacci sequence, which we remember hopefully from my first or second video on this channel, where we generated Fibonacci sequence in the top 16 bytes of the address space of the 8088. So I decided to repeat this idea in this test. So if we address port number 0 and use 16-bit transfer, we can get on each read from that port next Fibonacci sequence number. And the other kind of I/O port at address of 4 is even more boring. It just returns constant data. So the lowest byte is 45 and the highest byte is 23. So theoretically, if we run a program on 8188 and we do in AX from the port number 4, we should get 16-bit number in hex 2345. If everything works, we'll see it in a second. And all the other ports, which we didn't define here, just return FF because we need to return something. But just to test writing to the port, I also defined that if you write to the port of address of 0, it will reset the Fibonacci generator, because without it, every time we read from the port, it will generate consecutive numbers of the Fibonacci sequence. But at some point, we may decide to read again from the first number 2. So if you want to do that, you just need to output any value to address of 0, because we ignore the value being written to this. It's just to test writing to the peripheral. And that's pretty much it in this C code. So just to wrap it up before the test, we have two I/O ports, 16-bit I/O ports. At offset 4, we just return constant data. Writing doesn't do anything to this port, and the port at index 0, which reads consecutive numbers from the Fibonacci sequence. If you want to reset the generator, you just write to this port any value, and that's it. Now let's try to execute everything and check if it works. Okay, let's finally test the whole idea and the PIO program in our Pico using the step-by-step mode. Before we actually turn on the computer, let me just explain those wires to the text LCD. I decided to not using the direct connection because it was too slow. The text LCD is too slow to talk to the CPU, so I decided to use the text LCD only via the 8255 GPIO pins. And I also updated the code, the driver for our LCD. You can find it on my website on GitHub. As always, I decided to use only 4 bits because the text LCDs can be driven using all 8 bits or 4 bits, which obviously requires twice as many transactions kind of via the pins. But I still decided to do this. The code is configurable, so you can switch it to 4 or 8 bits, and you can also switch and use different ports A, B, or C and different pins to drive all the signals to the text LCD. So that's updated. You can check it on my GitHub. and I will be using for this test the new code here. Okay, I think it's time to test our idea of the Pico as an I/O device. So as you saw in the code, I defined a few ports within the PIO, and from the listing you can see that I'm stopping our CPU using the int3, which is the debug interrupt, to switch it into the step-by-step mode. So after the whole initialization, it'll stop at address, I guess, 6C. Okay, let's run it. Oh, look at that, 006C. So as I said, we are now paused before XOR AX, which zeros the AX. So let's step through this. Yeah, the AX now contains 0. And the whole idea is to check if the reading from an I/O in Pico works at all. So I defined, as you remember, two ports with the offset 4 and offset 5. One returns, I think, 4-5 hex. The other one returns 2-3 hex. So we are reading now to the AL value from the port number 4. If we step through, we can see that the 4-5 is returned from the Pico. Again, this instruction just read a value using I/O address space from the Pico. The Pico returned value 4-5. If we step through to read the kind of older byte, you may say, if we treat these as 16-bit value, it would be 2-3, but still in AL. Now the next test from the listing is to read the whole value as a 16-bit integer. So first we zero out the AX again, and the next instruction, as you can see, is not in AL, it's in AX. So it's a 16-bit read. It will read port 4 and 5. It will return the whole 16-bit value into the AX, hopefully. Let's read that. And yes, we have the whole value 2345 in the AX currently. Next test is to use the port at the offset 0, which is the test I kind of borrowed from one of the first videos on this channel, which was to return consequent values from the Fibonacci sequence. So we zero out AX, but before we do that, the first instruction loads 20 or 1/4 hex to the CX, which is the counter register in the loop. We've got 1/4, so we're gonna see 20 Fibonacci numbers in the AX. All of them are 16-bit wide, so we improved from one of the first videos from 8-bit to 16-bit. Let's see the first value in the AX, and there you go. The first value is 2. Then we decrement CX, and if it's not 0, we go back in our loop to offset 7-9. And then we read another value of the Fibonacci sequence, which is 3, and that's how the loop works 20 times. We were reading only in our test, so I also defined that if you write anything to the same port 0, it will reset the Fibonacci generator. So after you've written anything to the I/O port at offset 0, it would reset, and the subsequent reads will read Fibonacci sequence from the beginning, from number 2. So we're in the last pass of our loop. So we just zeroed out the AX, and in the next step at offset 80, we're going to write it to the same I/O port, to our Pico, to let it know that we want to reset the Fibonacci sequence. No, it's not very useful, I know. It's just a test of whether the reading and writing both work when we talk to our Pico. So we are now writing. The Pico should now see, oh, they wrote something to my port, so I will now reset the sequence. And now we're getting into the next very similar loop with just 10 iterations this time, so A hex, and we read the first, again, Fibonacci number, which is 2, then 3, then 5, and so on. So that was just a test that the whole hardware and our PIO program inside the Pico works and can effectively talk to our ATC188 like any other peripheral. In the next video in this series, we will start maybe using SD card, we'll see, as the hard drive will make some tests as well, so I hope to see you there. Take care and see you next time.